Now I want to talk about even and odd functions. So the first thing to keep in mind is that when we talk about even and odd numbers, every number, every whole number anyway, is either even or odd. That's not the case with even and odd functions. Some functions are even, some functions are odd. Most functions are neither even nor odd. But even and odd are two special kinds of functions. So we're going to talk about some different ways we can tell them apart by their graph, by their equations. But first, let's talk about their graphs. So even functions are symmetric about the y-axis. So the y-axis is right here, and an even function is symmetric about the y-axis, meaning that the y-axis is a mirror and it's the same on either side. So looking at these two functions, do we see one where it's even, meaning where it's symmetric about the y-axis? So the y-axis acts like a mirror and it's the same on either side. So if you said this one, you're right. So this function is even because it's symmetric about the y-axis. So that means that the y-axis acts like a mirror here, right? And it's the same on either side of the x-axis, right? It's the same over here as it is over here. This acts like a mirror. So this is an even function. Now an odd function, you can probably guess that odd function is over here. So an odd function is symmetric about the origin. And what that means, so odd is symmetric about the origin. And what that means is that if you think of turning the function by 180 degrees, it would look the same. So it looks the same in the first quadrant as it does in the third quadrant. But if we rotated this whole function by 180 degrees, and let me actually see if I can do that. So if we rotated the function by 180 degrees, like this. Oops. So it's not coming quite back to the same spot, but you can see that the function looks the same. And now I'm going to keep going so we can go back to the original spot. So when you rotate it at 180 degrees or flipped it over, it should look the same as how it looked in the first place. And I didn't quite get it lined up just right, but you can see that as I turned it around, it looked the same. Okay, so it should be symmetric about a 180 degree rotation. Okay, so you can also tell even and odd functions by their equations. So let me go ahead and get rid of this stuff. So just try to get rid of that too. That one doesn't want to go away. Okay, let me try one more time. Okay, I don't know why that one doesn't want to go away, but that's all right. We'll just leave that one there. We still have plenty of room to write now. So an odd function, when we write it in its f of x format, so like f of x equals x to the third plus 3x, something like that, an odd function has all odd powers of x. So an odd function has all odd powers of x. Now you might be thinking, what's this power of x? Well, it's really x to the first, right? If we don't see it, it's really x to the first. So it has all odd powers of x, meaning that it can't have any even powers of x. So you don't want to see an x squared or x to the fourth, and you can't even have a plain number And that's because a plain number, just a constant like plus 4, that is actually x to the 0 power, so that's an even power of x. So as long as it has all odd powers of x. Now notice, this could be 4x. It doesn't have to be all odd numbers. Even numbers are okay, just as long as all the powers of x are odd. So even numbers are okay. This could even be a 2. Even powers are just fine, as long as we have all odd powers of x. So even functions are kind of the same. So even functions have all even powers of x. For example, f of x equals x to the 4th plus 3x squared plus 7. Now remember that this is actually an even power here because it's really x to the 0, right? X to the 0 power is 1, so we can consider this to be an even power of x. So this is kind of extra, right? We don't really need to write that, but you can think of that as an even power of x. So again, it doesn't matter if the coefficients are even or odd, it just matters that the powers of x are all even. And now remember again that the vast majority of functions are neither even nor odd. So most functions are neither even nor odd because they contain even and odd powers. So, for example, f of x equals x squared plus 3x plus 2. Well, this has an even power, but it also has an odd power, and then it has another even power here. So it has odd and even powers, and then it's not either even or odd. So all the examples that I've given you have been polynomial functions, and eventually we will talk about different kinds of functions and whether they're even or odd also. But for now, we'll just stick to polynomials. So those are some different ways of telling if functions are even or odd. There's one more way that I want to talk about. So let me get rid of some of this. So if we have an odd function, one test of an odd function is what happens when you plug in f of negative x. So let's just take an example. F of x equals 3x to the 3rd plus 4x. Okay, so if we put in f of negative x, we're going to get 3 negative x to the 3rd plus 4 times negative x. And this gives us 3. Negative x to the 3rd is just going to be negative x to the 3rd, right? Because that negative power is going to be multiplied 3 times, so it's going to stick around. And this is going to be minus 4x. So this is going to be negative 3x to the 3rd minus 4x. So f of negative x is equal to negative 3x to the 3rd minus 4x. And you can see that this is the same as multiplying the entire function through by a negative 1. And that's true of all odd functions. So for all odd functions, if you plug in f of negative x, it should be equal to the original function, but everything is multiplied through by a negative 1. So f of negative x is equal to negative than whatever the original function was. And that's true for all odd functions. So if ever you have an odd function, any kind, polynomial or not, and you plug in a negative x, that negative should carry through to the entire function and make every piece of that function also negative. Or it should be like multiplying the entire function by -1. Now, even functions behave differently. So let's do an example of an even function. Let me go ahead and erase. Let's do this. I'm going to erase this part. And then I'm going to move this part. Oops, that's not what I wanted to do. I'm going to just move this part up here so that we can keep that around. Okay. So now I want to try an even function. So let's take f of x equals 3x squared plus 2. That's an even function because it has all even powers. If I take f of negative x, I'm going to get 3 times negative x squared plus 2. So this is 3, negative x squared is just x squared. So x squared plus 2. So f of negative x is equal to 3x squared plus 2. Well, that's the exact same thing as 3x squared plus 2. So this is what happens in even functions. F of negative x is equal to f of x. So it's just the same. You can plug in a negative number, a negative x, but it doesn't change the function at all. And if you think about that, that is the same thing that's happening here, right? If we put in a negative number, it comes out the exact same as a positive number. If you put in -1, it comes out in the exact same spot as +1. If you put in a -2, it comes out in the exact same spot as a +2. And that's what makes it symmetric about the y-axis, because all the negative inputs give you the same value as their positive inputs. And so anytime you plug in a negative x into an even function, you should just get exactly what that function was. It shouldn't change it at all. And so that's another way to tell even and odd functions. But remember, most functions aren't going to behave like this. Most functions are neither even nor odd, but there's some special functions that are odd and they'll behave like this, and special functions that are even that will behave like this.